Welcome to this session. So, as we are discussing that we were looking into the batch cell dialysis system, and we are trying to model the batch cell system. The purpose was to evaluate a parameter, that is the solute diffusivity in the dialysis membrane, DIM. Once that will be evaluated, then we are in a position to obtain the all the coefficients of all the components of the overall mass transfer coefficients, because from the definition of mass transfer coefficient in the channel, we will be evaluating the resistances or mass transfer coefficient in the feed side, we will be evaluating the mass transfer coefficient in the dialysate side. So, if we can evaluate the membrane resistance, that DIM by L inverse of that, then we will be in a position to find out all the three components of overall resistance, and overall, therefore, we will be evaluating the able to find out the what is the overall mass transfer coefficient. So, in order to do that, we have conducted an experiment in a small batch cell, where we are putting the chamber, the feed and the dialysate sides will be separated by a semi permeable barrier, and in the feed side we will be putting the solution side. In the dialysate side, we are putting the dialysate solution, and the solute will be being transported from feed side to the dialysate side. And what we will be doing, we will be taking up samples periodically from the dialysate side, and then we will be measuring its concentration. Once that is done, then we will be comparing the profile with the theoretically calculated profile of the dialysate solute concentration in the dialysate side, and then we will be evaluating the value of diffusivity across the in the membrane matrix by the solute of I. So, we have written down the mass balance equation in the dialysate side, we have written down the mass balance equation in the feed side, and we have set the boundary condition initial conditions for both the equations, and Vd and Vf were the volume of the feed side and the dialysate side respectively, and they are treated as constant. So, these two equations can be solved in many ways. One of the method is using the Laplace transform. Then these two equations, ordinary differential equations, will be boiled down to algebraic equation, and it will be easier to solve. If we use a Laplace transform, apply this transform to governing equation in dialysate side. If we do that, we will be getting S C I D bar will be nothing but A m d I m divided by L V d C I f bar minus C I d bar. And if we apply the transform to the feed side, so this is the dialysate side, we apply the same equation in the feed side, we will be getting S C I f bar minus C I f naught is equal to minus A m d I m over L times V f C I f minus C I d bar. Now, we can take A m d I m over L is equal to constant K. M is the membrane area, DIM is the diffusivity of solute to the membrane matrix, L is the membrane thickness. So, the first equation becomes S C I d bar is equal to K by V d C I f bar minus C I d bar, and second one will be S C I f bar minus C I f naught is equal to minus K over V f C I f bar minus C I d bar. Okay. Now, these two equations can be solved, and we can get the expression of C I d bar. We can just replace C I f bar from one equation into the other, and by putting the values of this, then we can get the expression of C I d bar. I am just omitting two steps, they are very simple, two equations and two unknown system. So, C I d bar will become K by V d C I f naught divided by s square plus s k 1 over V f plus 1 over V d. So, that becomes the governing equation of dialysate concentration, solid concentration dialysate site in the Laplace transformed coordinate, transformed parameter or variable. So, once we do that, then we will be doing a further simplification. We will write A is equal to k times 1 over V f plus 1 over V d, and this becomes C I d bar is equal to k over V d C I f naught divided by A 1 over S minus 1 over S plus A, and one can get a inverse Laplace transform taking inverse Laplace transform. One can get C I d as a function of time as k over V d C I f naught divided by A 1 minus e to the power minus a t, and if you put all the constants etc. So, you will be getting the expression of C I d as a function of t is equal to C I f naught V f V d divided by V f plus V d 1 minus e to the power minus k 1 over V f plus 1 over V d times t. Okay. So, essentially these will give a curve something like this, C I d as a function of time. The curve will be starting from 0, then it will be increasing, and ultimately it will be reaching at higher value of t, it will be reaching a constant value C I f naught by this one. So, now if you look into this expression, everything is known to us, and what is k? K is nothing but A m d I m over L. Okay. So, we can fit a curve, or we can put a log linearized version. So, if you can do that, this becomes C I d is equal to C I f naught V f V d divided by V f plus V d 1 minus exponential minus k 1 over V f plus 1 over V d times t. So, we can rearrange it. This becomes 1 minus e to the power minus k 1 over V f plus 1 over V d times t is equal to V f plus V d divided by V f V d 1 over C I f naught C I d as a function of time. So, this becomes e to the power minus k 1 over V f plus 1 over V d times t is equal to 1 minus V f plus V d divided by V f V d 1 over C I f not C I d times t. So, we can take the log on both sides. So, if you get log on both sides, 1 minus V f plus V d divided by V f V d C I d t C I f naught is equal to minus k 1 over V f plus 1 over V d times t. So, if we so as time progresses, as we have discussed earlier, we will be measuring the solute concentration in the dialysate site. So, CID will be known to us. We know feed concentration of solute in the feed side, VF volume of the feed and volume of the dialysate are known to us. So, whole lot of left hand side will be known to us if we can measure the dialysate concentration at different point of time. Then if you plot this ln this versus t, it will be a straight line with a negative slope, and from the slope, what is the slope? The slope will be k times 1 over Vf plus 1 over Vd, and we know the volume of the feed and volume of the dialysate. So, we will be able to estimate the value of k, and what is k? K is nothing but Am dim over L. So, once we know the value of k, we know the membrane thickness from a SEM photograph, and dim will be nothing but the and Am will be nothing but the membrane area. So, we know the dimension of the two channels. So, the membrane area will be known to us. So, we can calculate estimate the value of dim. So, from this relationship we will be able to estimate the dim. So, this is the procedure to obtain the solute diffusivity in the membrane matrix. So, what we will be essentially doing, we will be conducting a small batch cell experiment as a separate part, and measuring its concentration in the measuring the solute concentration in the dialysate site at different point of time. Then we will be plotting the quantity that we have already discussed in the y axis and time in the x axis. From the slope we will be getting the value of dim. So, once dim will be known to us, then we will be able to estimate all the three components of overall mass transfer coefficient, and we will be able to find out the overall mass transfer coefficient. Then from the overall mass transfer coefficient, we will be able to find out the system performance. Okay. Next, we will be looking into the design of the we are in a position to design the continuous dialysis process. So, we will be looking into the continuous dialysis operation. So, in a continuous system, first we level all the stream and their concentration. So, this is the feed going into the system Fi, Ci, Fi. So, ith component in the going into the system Fe, Ci, Fe. So, ith component that is exiting at the from the feed, then dialysate going into the system. Di is the volumetric flow rate or the mass flow rate, its concentration is Ci/di, and this is d out is the flow rate. So, this will be Ci/d out. Okay. This is a counter current. Continuous dialysis operation. So, let us do the analysis, and the assumptions involved are, so it is basically one dimensional analysis. The assumptions involved are constant feed flow rates, one, two is the dialyzer performance, depends on value of film and membrane resistance. And then film thickness, of course, that is true. Film thickness depends on geometry and flow velocity, channel geometry or flow geometry and velocity profile. So, with these assumptions, let us write down the various design equations. So, design equations for a continuous counter current dialyzer will be the transmembrane mass flux of the species will be m I K0 overall, AM is the membrane area, delta C I LMTD. We are writing the mass flux of ith species. Okay. Then mass flux can also be presented as whatever the mass that has been gone from the feed side to the dialyzed side, the dialyzed side will be getting that amount. Okay. So, at the steady state, m I will be nothing but V f dot C I f I minus C I f E bar is equal to V d dot we call it L D dot C I d E out minus C I d I in. So, so this is basically the mass flux kg per unit time, hour or minute. V f dot is volumetric flow rate, of feed. L d dot is nothing but the volumetric flow rate of dialysate. C I f I is the ith, for the ith species, the concentration that is going into the system by the feed stream, the concentration of solute that is going out of the feed stream. So, C I d E is the concentration of ith solute that is going out of the dialysate side, and this is going into the dialysate side. Typically, this will be equal to 0, and the amount of solute that will be lost by the feed side will be the amount of solute that has been gained by the dialysate side. So, these two will be equal. So, next we define the dialyzer efficiency. Dialyzer efficiency is actual amount of solute depletion in feed divided by the maximum amount separated in a dialyzer. So, that is the definition of dialyzer efficiency, and if you really do that, so one can get that V f dot eta is equal to V f dot C I f I bar minus C I f E bar. This is the actual amount of solute that has been separated, and this is the maximum amount of solute V f bar C I f I that is going into the system minus L d C I d I that is going into the system through the dialysate system. But typically, in the dialysate stream, the concentration of solute that is going into the dialysate side will be equal to 0, and this part will be equal to 0 in most of the cases. And if there is some amount of solute that is going into the system, so this is the maximum amount of solute that can be separated, and this is the actual separation that is being occurring. So, that will be defining the efficiency of the dialyzer. So, using these equations one can get the expression of the one can design the dialyzer. So, also if you remember that the overall mass transfer coefficient can be defined as overall mass transfer coefficient in the feed side L by d I m plus 1 over mass transfer coefficient in the dialyzed side. We know the flow domain, flow regime and the geometry in the feed side. We can calculate the mass transfer coefficient in the feed side. Similarly, the flow regime and the geometry in the dialyzed chamber is also known. So, you can calculate Kd. DIM, for DIM we will be conducting a separate set of experiment in a batch dialyzer set under continuous high stirring or turbulence. So, that the we can estimate, we will be able to estimate the diffusivity of the solute in the membrane matrix only. So, once we know that, then we will be able to find out the overall mass transfer coefficient and we will be able to design a continuous dialyzer. So, once we do that, next item that we will be looking into a system where the enhancement of separation in dialysis can be obtained by associating a secondary chemical reaction. So, that means in a batch system what is happening is that the solute will be transferring from the feed side to the dialyzed side and therefore, enhancing the solute concentration in the dialyzed side. I am talking about a batch operation process. So, therefore, in a batch operation process the solute concentration will be continuously decreasing in the feed side and it will be continuously increasing in the dialyzed side. But in the dialyzed fluid, if we can put a chemical which will be reacting immediately with the solute that is arriving there from the feed side, we can maintain the concentration of that particular solute to be 0 at all the points. Thereby, we can maximizing the concentration gradient, the driving force across the membrane. Therefore, the solute concentration in the dialyzed side can be maintained at 0 concentration, thereby maximizing the driving force of the solute across the membrane. Once that we can do that, then the dialysis will be much faster, and let us look into the modeling of the batch dialysis, which will be aided by a secondary reaction. So, next we will be looking into the modeling of enhancement of separation in dialysis by secondary chemical reaction. Okay. So, we select we put let's say we give an example that aniline is to be removed, aniline to be removed using from feed side using dialysate as H2SO4. So, it reacts with aniline reacts with sulfuric acid to form anilinium ion. This anilinium ion being larger in size, they cannot get back into the feed site. So, therefore, in the dialysate site aniline concentration will be always maintained to be 0. So, this will be equilibrium Gaussian process. So, we call this component as 1, this is 2 and anilinium ion is 3 and component sulfuric acid will be always in excess in the dialysate site. Sulfuric acid or component 2 is always in excess, that means concentration of sulfuric acid is constant and its concentration is invariant with time. Okay. So, let us write down the mass balances then. So, solute balance in the feed, as we have done earlier, we write down the mass balance in the feed chamber and the dialysis side, solute balance in the feed. So, V f d C1 f dt will be nothing but minus A m d I m divided by L C I f minus C I d, and the system is under continuous stirring. Okay. So, under continuous stirring, this is the solute balance of component 1, this is 1. Okay. For component 1, so this equation can be rearranged as d C1 f dt will be nothing but A m d I m L times V f C1 d minus C1 f, and now we write down the solute balance, that is the component 1 balance in dialysate side. So, that will give you d C1 d dt will be nothing but A m d 1 m divided by L V d C1 f minus C1 d minus d C3 d dt. This will be basically the rate of consumption. The first term will be the amount of solute that will be arriving in the dialysate site, and the second term is basically the amount of solute that will be consumed because of the reaction, chemical reaction that is going on. So, we consider A m d 1 m by L should be equal to K. So, if I write it that, then we can shortly write the governing equations in short. d C1 f dt will be nothing but K by V f C1 d minus C1 f, and the other one is d C3 d dt plus d C1 d dt is equal to K over V d C1 f minus C1 d. So, these will be the final transformed equations. So, I will stop in this class. In the next class, what I will do, I will find an expression of d C3 dt, and then we will be trying to solving this set of equations and see what you get. Okay. So, I will stop here, and we will continue this problem in the next class, and we will finish it up. Thank you very much.